So welcome to the beginning of the new term and a new, I guess, world of Waterloo AI seminars. I'm Mark Crowley, assistant professor in the Electrical and Computer Engineering Department at the University of Waterloo here, and at the Waterloo AI Institute. So today we're going to be having our first talk of the term, and I'm just going to give you a little kind of overview of the Institute and then kind of introduce our speaker. So while people are signing on, whether you're watching us live or coming on later, the Waterloo Artificial Intelligence Institute is kind of a way that connects all the different researchers on campus into collaboration and connecting with the local community in Waterloo, in Ontario, in Canada, and all the different kind of research that's happening at the university. So I think you can see my website, the website I have up here, not my website, the Institute's website. It's that you go to waterloo.ai, you can see us, and the university has kind of a broad range of kind of research in machine learning, AI, software engineering, which can relate to today's talk, but also human-computer interaction, autonomous driving, nanotechnology, quantum computing. There's a huge range of research that intersects with AI and machine learning in many places, and that's the kind of thing that the Institute connects to. So for those of you who haven't seen us before, welcome. For those of you who used to come to our talks before the world went crazy, welcome back. Nice to virtually see you. And so what we're going to do now, we're going to have a range of talks over the fall. We haven't announced them yet, but we're kind of working on some great speakers. If you have ideas of events or speakers for the Institute, please let us know. Myself and Professor Yao Ling Yang in the computer science department kind of organize these seminar series, but the Institute does a whole bunch of other stuff connecting with local industry and funding sources and community to kind of expand AI in the region. The speaker today is Professor Ashkan Sami, who's going to be talking about dependability and security and improving both at the same time for kind of software projects. He obtained his bachelor's in engineering at Virginia Tech and his PhD from Tohoku University in Japan. And he's the National Lead Foundations Professor as of last year, and he's been kind of regularly presenting on BBC and Stack Exchange in the Register with some of his ideas on software understanding and analysis. And so he's going to give us a great talk today about his research and looking for connections, I think, with more AI workers research in the community. If you have questions along the way, just feel free to chime in and I can kind of moderate them, and if they're urgent we can ask them as we're going, but otherwise we'll have some questions at the end and have a nice discussion about it. So without any further ado, Professor Sami, the floor is yours.
Thank you for giving me time, and it's an honor to be here presenting virtually. My talk will be a little bit different from the regular AI-based talks. It's more empirical, but there are a lot of topics and I'd like to have collaboration with, and I hope this talk will initiate some interdisciplinary research in the area. So with no further ado, I'll start talking about my presentation. Today, talk will be a bit different because I'm addressing somehow empirical study research, and I will talk about dependability and security in systems. Dependability, usually we talk about something that system reacts properly and you can rely on, but security is usually a mechanism. So when we think of dependability and security, they somehow seem contradictory to each other. And in this talk, I will try to show the path that we pave that we can improve both at the same time. I'm from Shiraz. Shiraz is the south city in Iran. And this is Iran, near Afghanistan, Pakistan, and Iraq. This is a picture of my university. I thought you would like to know it. And this is where I actually go to work. We are among the top 500 university departments in the past 3 years, based on Times Higher Education ranking. So with no further ado, I would like to talk about the definition and motivations for the talk. And I will show 2 parts and how we can improve security and dependability. First, by secure coding, and second, by re-ranking vulnerabilities. Cyber physical systems are all around us. They are the systems that are built by seamless integration of computation and physical components. CPS are data-rich, enabling new and higher degree of automation and autonomy, which involve pretty much all areas of software engineering, data science, mechanical engineering, electrical engineering. But the problem is traditional ideas in CPS research are being challenged by new concepts from AI, and the integration of AI will create a very different scenarios and with major societal implications. That's where I got very sensitive, because we're not talking about physical systems, we are talking about software-intensive systems, systems that have AI embedded in them, and a lot of decisions that they make may cause safety concerns and can cause damage to environment or physical life. Just since I didn't know the range of audience, first I talked a little bit about the basic definitions. I apologize if this definition seems very basic, but just to make the common ground, the dependability of the system reflects user trust in the system and how confident it is that it will not fail in normal operation. Dependability is usually contributed to several attributes. They are not commonly, there is no common consensus on all the issues. But one definition, and by some of it, was based on availability, reliability, safety, security, and resilience. Availability means system is up, running. It doesn't mean it provides the necessary service. Reliability, in contrast, it means it provides the service that is needed. Safety means the ability of the system to operate without catastrophic failures. It doesn't kill anybody, it doesn't cause endangering human lives, or it doesn't cause problems to the environment. And security, as we all know, the ability to protect system to protect itself from deliberate or accidental intrusion. But the pillars of security are based on confidentiality. When we think of security, we usually think of confidentiality as the most important issue. We don't want our information to be disclosed or made public to the people, or unauthorized access of the information to the people we don't trust or we don't want. Integrity is the second most important in IT systems, which means no damage to the data, or no change or no modification when we retrieve the data or transfer the data or store the data. In contrast, when we think of security, availability is the last thing that comes to my mind as the most important issue. We all had scenes that we restarted our systems after a problematic issue. Well, some people think that when we talk about malware and when we talk about security, we should only focus on malware research. That's what we did too. Actually, I and my team, we created the first open source malware dataset for academic research about 10 or 11 years ago. We did a lot of research, AI-based research on how we can detect malware. But It's like this is another application that we created features that were very good at detecting malwares based on the runtime environment. But when we analyzed, I mean, when problems and new kind of attacks on CPS and cyber physical systems started, we start analyzing what the major part of cyber physical systems are, and that is SCADA. SCADA is supervisory control and data acquisition. It's a software. Basically, first it's a software, and it's the software that collects the data and sends the supervisory control signals. We did not have access to industrial applications. Thus, we searched what are the open source applications, and we tried to analyze them by various static analyzers. Interestingly, we found the number of critical bugs were much higher than we thought. This work is done back in 2013, and that was the main motivation for a lot of things I talk about to you today. So the open SCADA had like 1,500 or 1,400 files. Among those, it had more than 200 seriously vulnerable files, around 14%, and critical bugs, nearly 20%. We checked another open SCADA. These have the same name, but they are completely different because they are in different languages. Again, number of critical vulnerabilities and the percentage of files that had critical vulnerabilities were much higher than what we expected. We did that in other open source SCADA systems, and we came up with the same numbers. I mean, we are talking about a software application that controls a company, controls a plant, controls a very critical structure. And these open source, like MNDACS is another one, all of them had very serious critical vulnerabilities. I need to say this, static checkers usually give much more, I mean, more than just critical vulnerabilities. They have a lot of false positive in a sense, because they don't want to miss anything. They don't want anything to miss. But other sources, and so when we checked the SCADA systems, we noticed a lot of them have a lot of vulnerabilities, and these applications are actually the ones that are controlling everything. So I thought, if I want to improve security, if I want to improve dependability, they must start coding correctly. You cannot build a house and then start fixing the walls after you've built it. So the first layer was secure coding. To reach out and focus on secure coding, we started several teams and we looked at several aspects of the problem. Stack Overflow is the main place, is one of the most popular question and answers that software developers use. So irrespective of what software developers would like to create and would like to build, the applications, the developers of applications usually ask their questions in Stack Overflow post. And as you can see, a large portion of developers in the United States and are in United Kingdom that are using Stack Overflow. Basically, Stack Overflow post a person who wants to ask a question, post the question with a title and a description of the problem task, and people come and vote to the problem. It has dates that when they asked, also who asked this question, and people come and write comments, and also tags will clearly tell what this question relates to. The knowledge sharing in Stack Overflow is tremendous. There is a lot of collaboration going on. Code sharing is very common, and reusability of the code is prevalent. And a lot of scientists and programmers want to improve their code by searching through Stack Overflow. They discuss best practices, they find fixes for bugs, they offer suggestions and improvements. So basically, when a person asks a question, another developer answers, and the answers, they may have several accepted answers by the questioner or by the asker, and so if it gets an accepted mark, so it is a very good question. So the developers actually use these codes and they create Git repositories and they deploy and build it. And if they notice a bug, they notify the developers through the mechanisms Git provides. But the problem is, if you come up with a vulnerable application, vulnerable code segment, it can go to production. It can lead to exploit by hackers. So we chose C++ because C++ is the system programming choice of embedded systems, and for CPS, basically a lot of CPS, SCADA systems, a lot of embedded systems are written with C++. It is also one of the most popular languages, and for a lot of large system applications, it is used. Interestingly, nobody investigated C++ vulnerabilities in Stack Overflow, and it created more motivation for us to follow the path and see what's going on in this problem. Just to tell how we can actually tag a vulnerability, there is a mechanism by Metric Corporation, there's a standard by Metric Corporation that is called CWE. It's an abbreviation for Common Weakness Enumeration. Common Weakness Enumeration tells what kind of vulnerability exists in the code. For example, for this code, we have 3 types of vulnerability. We have obsolete function like rand. We have off by 1 error. The length of the string is len, but after we exit this loop, we give it a value, so it is 1 after the length, the proper length, and improper check for unusual exception, because if we use this number, we may have a couple of null values in SI, and it's an exception that is not handled. So CWs usually come with description, the scope, it means it attacks integrity or availability, and what kind of impact it has, and they also sometimes provide mitigation strategies or mitigation methods. We wanted to look through 10 years, and we wanted to look through history of Stack Overflow, so we can talk about the evolution of vulnerabilities that have migrated from Stack Overflow to the GitHub. So we used SOTorrent database. SOTorrent is basically a set of tables that collects all the dumps from Stack Overflow from 2008 until now. So we only used 2008 until 2018. That was the period of study. So we had not only the current post, we also had all the modifications to the post. They used a lot of heuristics. For example, they separated text from code and code from text. And this is something I think AI community can help a lot, because in software engineering and security problems, still understanding these code segments are actually code segments is a question that is not quite properly answered. There, we answered it somehow through our research that I will explain. So we were not only interested in what vulnerabilities exist, but we wanted to know, as I told you at the beginning, I wanted to know what happened that vulnerabilities lead to very vulnerable projects. So we focused on Stack. SOTorrent actually looked through GitHub project, and they brought all the links to the SOTorrent in the GitHub projects, and they stored it. So by looking at the SOTorrent dataset, we could focus on the posts that had direct link in GitHub project. In other words, in one of the data sets, like some of the posts were stored and history was stored, they had a table that stored the link between the GitHub projects who referred to its author. So basically, we checked the related work, and there were a lot of work on Stack Overflow because it's the main platform for sharing code. A lot of researchers spend a vast amount of time on various aspects of Stack Overflow, like code sharing. Also, regarding security of code snippets, researchers talk about the Java, the Python, and even web application, Android, and even documents. For GitHub, definitely security problems were observed, and there were some people who looked to it because it was the main platform for open source projects. But we couldn't find any work that was on Stack Overflow C++ vulnerability. We couldn't find any work that watched and looked through the evolution of vulnerabilities within Stack Overflow for 10 years. We couldn't find any work that looked at C++ vulnerabilities migrating to real projects. So the migration from vulnerability from question and answer to GitHub projects were not extensively studied, and especially how the developers will react. So I really wanted to know if I could fix the problem by my research. And so what we came up, we thought, okay, so we should take Stack Overflow data and extract only the code snippets. But as I said, the code snippets, the heuristics used are not perfect. So we have a lot of code, we have a lot of snippets that are tagged as C++ codes that are not actually. And since the whole history of tag is stored in a way that any modification, the whole post is stored in all tables in a software. And so we had a lot of copy and redundancy in the code. So we had to find the common ground and only unique codes. And after doing that, we needed to review the codes very extensively and very restrictively. So we make sure there are some vulnerabilities that we can point that have migrated to real world applications. Among the 41 million question and answers with the over 109 million version history of those, we noticed about more than 500,000 C++ questions were presented that received over 1 million answers. With the history of those answers, that is all the modifications through the 10 years, we had 1,740,000 answers that migrated to more than 1,700 GitHub projects. So these are the distribution of those. And as I said, we had to do some NLP, and we had to do some TensorFlow-based syntax parsing framework to come up with C++ code snippets that were actually code snippets. That is, we had something like this, that's not a code, but it was tagged as a code. And after we ran the algorithmia on our analysis, the 121,000 code snippets that we were looking reduced to 72,000 actual C++ code. So this study analyzed 72,000 code snippets within the Stack Overflow history. And so we used a clone detector. Clone detector is basically find similar codes, and we wanted to know among these 72,000 code snippets, how many unique codes we have. Just as a brief introduction, if this is the source code, if we have just adding comments or simple modifications like comments, we call it the type 1 clone. But if we have lexical similarity, like the algorithm is pretty much the same, but we have some renaming or variables are changed, we call it lexical. So it's type 2. Type 3 is semantic. We only focused on type 1 similarity. And among the 72,000 code snippets out of 1,300 answers, we notice only we have 2056 set of data. I mean, so we manually checked through every single code snippets of these 2000 plus code snippets, a snippet of a code. And after several rounds of review, and as I said, we were very restrictive. We read the corresponding question answer. We read the last version of the story. We read the comments, like these comments, they say the S length is improperly tagged null. And then we looked through dangerous functions. We checked the argument passing. We checked the function. We checked the official documentation. Very rigorous. We wanted to make sure the vulnerabilities are actually vulnerabilities. And we came up with 90 with samples of like this, that, as I said, they have obsolete functions or off by one or improper check, or this one that has vulnerability of null pointer dereference, means it used a pointer that had null value, or we had in this code snippet, you could enter any command, and this code snippet executes this with the proper authority. So we checked that, and we found several type vulnerabilities within the data set that we were running, and actually we came up with 69 actual vulnerabilities in 69 answers, code snippets. So maybe you say, 2,000 codes you reviewed and you barely got 100 vulnerable answers. So the fraction is like 4%. It's not important. But the important ones, those, and these are the distributions per year. So this is like in what years those occurred that I pass, and these are others. So the problem was, and what we were looking at, how these vulnerabilities migrate to GitHub projects. Interestingly, we found these 69 answers go to over 2,800 projects. And that is a big number, very large number. Out of 69 vulnerable answers, those 69 go to 2,800 projects. It means when you are sharing a code, it can propagate very rapidly, and it can create vulnerable applications a lot. Just because, again, we were very restrictive study, we used a heuristic. It was a very unique heuristic. Again, this is a part that the AI community can help to find various variation of vulnerable codes and searching into the projects. That can help a lot. We are still missing that part. And anyway, based on our heuristic, very restrictive heuristic, we got 287 detected out of these. And we again did a manual code. These are distributions. And after extensive review, we found 253 vulnerable GitHub projects were detected. And some of those were actually fixed. Like this one, they fixed the checking boundary, or also this one, the checking boundary. And these vulnerabilities were all fixed, but 253 was used. So here, we created an issue. We were happy. Okay, now we found 200 something projects. Now we let the developers, okay, you have a problem, and they would be happy. They will tell us, okay, thank you very much, and we provided a very descriptive issue. We tell them what the example of this is, how the migration is. We provided an official documentation reference, but it didn't turn out to be what we thought. We told the developers you have problems. We told them why we think they have problems. We provided official documentations showing why they have problems, but only 13% of the respondents said they have fixed it. 13% said, no, we don't have the problem. We don't want to fix it, very clearly. 6% said the code was public. So about a fifth say we don't know, and 2/5 said, well, it is safe. Input is not dynamic. So we asked them, how we can help them, and if an automated vulnerability analysis check can help them. And they said yes, if it would be nice to have an automatic code checker. So we provided actually an extension, browser extension, that can pinpoint to vulnerable codes. But the problem rose, and the problem stayed, actually. I mean, we also checked the Sorcerer CC and all the review processes that I pass because of the shortage of time. You can call me, I'll explain what they are. But my main concern stayed. I mean, we have a lot of vulnerabilities in the code sharing platforms, and they are copied and pasted, and I couldn't inform anybody. Even the project owners are not listening. So I was really concerned how I can tell people don't do it. Fortunately, the paper just got accepted. This is a week, but before that, I made a preprint, and in the preprint, and I just wanted to say, okay, you have problem, and this problem should be answered. It got attention of several news agencies like Register. I was very lucky to have a call from Register, the Register newspaper, and they had an interview. So I said, please try to learn secure coding, and there's no easy way to code. And after that, fortunately, BBC had a coverage of the idea. And the good thing that happened was after BBC, a lot of people in Stack Exchange, which is a platform for Stack Overflow developers to talk, they start discussing the paper, and I got the voice widespread. It was heard widespread. And more interestingly, the Stack Overflow managers contacted me, and we had an interview, and I told them my concern, and they had to react. And so they put blogs, and several blogs, what the problem is and how the problem is published. So I hope to get better. I'm not sure, but we did another research on C#. It is just published in one of the fairly high-ranked software engineering conferences. And in this time, we focused on C#. It is a maintain type language. It doesn't allow pointer arithmetic. It doesn't have the problem C# has. It is safe. It checks. It has a common language runtime, and the common language runtime doesn't allow to have memory problems. But you can use an unsafe code, and I say unsafe context, and in the unsafe context, you can actually run any code. And it was given, so in case that you want to do pointer arithmetic with within your program, you use it. Again, we didn't see any study on C# on Stack Overflow, especially security, because it is a very safe language. But we wanted to see if the unsafe context actually creates a problem, and the codes are what kind of usage they are, and if they are safe, and if people know what they are doing. But again, and interestingly, we found majority of the unsafe codes, they don't even properly post the tag. We found less than 600 posts having the unsafe tag, but over 600 posts do not have the proper tag. And more interestingly, we found they use it for image processing, for interoperability, for memory access, like stack allocation, performance improvement, pointer, and memory management. But the the sad point of this is they use like some of the way they use like a stack alloc, which is used in unsafe. It is not recommended by the Microsoft to use it. And when you use unsafe, you are told that there is no checking on the memory. But after we analyzed all that, and I'm going to go to the statistics, we found that people are using dangerous functions within the framework that there is no check. And more sadly, we found the image processing code snippets that use unsafe for performance are not the developer's main concern in the framework. And they decrease the security, improve the stability. P-invoke was the main problems. P-invoke, what Microsoft doesn't want you to use it in unsafe. It gives a design warning. It tells the developer don't use it, but still we found a lot of people using it. So from the first perspective of the study, actually, and these are some of the codes that the improper adherence to coding standard, use of prohibited code. We found several examples like rand again here, and as I said, several examples we found. So in the first part, I suggest and I hope that when we want to improve dependability in a cyber physical system, we teach our control system engineers, and we teach our developers to write secure codes, to write properly. And this is not practiced. As strange as it may sound, the basics are not followed. So the second part of my talk, I want to talk about how we can improve security and dependability by re-ranking vulnerabilities. Again, as I said, we can look at IT securities versus cyber physical system priorities. But in cyber physical system, priority is minimal latency. You have to support systems that may last for 30 years. When you buy a car, you may use it for 15 years or more. They have safety concerns. The systems that we are using, they may kill you if they are not correct. They must be, any solution that we provide must have a reasonable cost and minimal modifications. I mean, how many times you can change the computer system within a car that you are using? How many times you can go through ECU and change everything within that? And the standardization is so complex. I looked at Industry 4, I looked at WWW, I looked at several frameworks that are used in industry and in security and in IoT. Interestingly, they are contradictory and they cannot be implemented altogether. So what I thought, and in critical infrastructure, CPSs are used widely. And this is like the data for 10 years ago. And you see the number of industries that are attacked by cyber security attacks. So the problem, and the problem needs and requires a specific solution for itself. When you are in IT platform, availability is not important. Confidentiality is the most important thing. You don't want to lose your credit card numbers. You don't want to lose your account number. You don't want to be changed. You don't. If you have $1,000, you don't want to wake up and see if it turned out to be $10. But who cares in a car network that what ECU is passing to the generator, or the ECU is sending to the cruise controller, the main packet, or the data that's sending or receiving. But if the brake system must work and it's not available, it can lead to safety problems. In other words, when we talk about IT, it must be fast, but in CPS, we have hard real-time limits. Availability is not very tolerable in IT, but in CPS is intolerable. Confidentiality is very important, which is in CPS is not important, and safety is very important. And lifetime of technology is very long, and patching is very slow, and antiviruses are difficult to implement, and security awareness are very, very poor. I mean, in IT, I'm sorry to say that, but control engineers did not have a single course in IT. So how can they know what to do and what not to do? And change is very difficult. After you build a car, how are you going to change it? How are you going to add a new packet? I mean, we can think of like adding systems like we did, like we added IDS, like this one. Actually, we've thought if we come up with the signatures of all attacks, because in cyber physical systems, the states are finite. We can come up with a finite number of attacks. This is one of the best journals in control that we try to address. And the problem is, number of states are very large, but they are limited. So if we can detect what multivariable metrics can lead to a problem, and we get all these numbers and all the large number of states and their combination, we can control them. But the problem is, a native approach will produce a lot of candidate states, but based on a well-known a priori algorithm, we can produce a complete solution. We can look at the answers, and we can come up with solutions. For example, first you check every variable, every state, and you see which one is critical, so you just leave it out. Then you combine the rest, and you create 2x2 combinations. Again, by help of security experts, you can leave out the ones that are critical, and you continue to the third iteration and go on and go forth. And we simply showed the iterations from 19 iterations, and the number of candidates reduces significantly, very fast to the whole state. But the problems of these kind of things, the mechanisms that you are adding, they also add mechanism, and they add to the response of the system. So basically, they are causing availability problems in a sense. They add and they take time. So we created a test bed for our system, and we simulated the attack system. We used actual control network systems, actual PLCs. PLCs are computer industrial control system. And we implemented one type of state base. I mean, we assumed what the state of like a milk pasteurizing system is, and we ran it. We simulated on a lab view, and we also published it in Critical Infrastructure Protection. Just in 2018 was published. After 2 years, it got on there. But again, these are mechanisms. So this is the work I would like to that we can some sort of modified secure coding practices in industrial applications, and by re-ranking the vulnerabilities. So this is published in 2016, but this is not a work that got the attention I really liked it to deserve. As I said, the priorities are in two different directions. So what we thought, if we look at the software applications, you may feel that some problems like overflow, the vulnerabilities that may cause you go and corrupt heap or corrupt stack are one type of categories, that they are in top tier of the categories. User input, another type of vulnerabilities that are in categories of CWE has top 25 dangerous vulnerabilities. It published in 2011, in 2019, and even recently, just recently, published 40 top vulnerabilities. If you look, you see overflow, you see user input, you see information leakage, the vulnerabilities that expose information to the system, and you see hazardous functions, the functions like getS that run all over the stack. I mean, if you put a very long input, it writes it to the heap or stack, and it overwrites all the important information. But if you look at all those important vulnerabilities, you do not see memory management as top vulnerability problems in IT systems. What are memory management problems? The vulnerabilities that cause improper release or not releasing memory resources. basically, what we thought we should change this. It is important to have an overflow, even in CPS. It is important to have user input, less important, but it is very important if you have if your resource consumption is not doing well. I mean, if you keep getting and you are getting memory and you're not releasing it, you're allocating memory and you're not releasing it, or other resources, CPU, RAM, anything, and you have a corrupted memory management problem, it can lead to stress problems for the CPS. It can cause availability degradation and reliability as a consequence of availability degradation. So we set up an experiment, but the problem was, okay, now I claim I want to fix security, I want to improve security, and I want to improve availability. But the problem was, we didn't have a metric to quantitatively assess whether availability is actually improved. We did not have anything. And we searched all over the internet. We searched all the problems. There were a lot and extensively a lot of work on hardware and how to assess availability. There are a lot of metrics for it. You find mean time between failure, you find mean time between repair, then you divide mean time between failure divided by mean time between failure and mean time between repair, the addition of these two, and you come up with availability numbers. But what is it for software? How can you assess whether the software is more available than the other? Software is nothing, is not a single commodity. It's not something conceptually unique. Software works on an OS platform where OS is working on hardware and it's serving services. So you have layers and layers of interacting components. How do you assess that? How do you come up with a number that, okay, now this software is more available than that software? You cannot use settings like hardware. I mean, for coming up with numbers for reliability of lamps, they set up experiments. They take like 100 or 1,000 lamps. They keep turning it on and turning it off and check when some of them, they go out of service, and they come up with some numbers. Well, we didn't have that, and we cannot do that for a software. I mean, you want to use a SCADA system, you want to use a software that is controlling the factory, and what are you going to do? How do you know this? And if something happens, how do you know if it's from the software, if it's from the OS, if it's from the interaction? So we had nothing to quantitatively assess whether the claim that we were making were actually correct or not. So we thought and came up with 3 metrics. They are open for discussion. That's what we hoped, but nobody actually talked about it and discussed our ideas, or at least improve it. So we thought we set up an experiment, and based on the experiment, it was a filling, actually small-scale filling system with 2 PLCs in the switch and the star topology. We used actual PLCs of Siemens S7300 and used star switch. This is the actual setting we used in advanced control laboratories at Shiraz University. This is the actual PLC that is widely used throughout the industry, especially in Iran, Siemens 300. And this is the open SCADA that we try to compare the secure version over unsecure version. As I told you, the static analysis of open SCADA led to a large number of vulnerabilities, much higher than what we thought. And the number of files that we had problems or were actually enormous. 35% of the files had problems in total. So we thought, instead of solving everything, first we looked at, we categorized the problems, and interestingly, a vast number of memory management problems, Because as I said, even in the mindset of the programmer, memory management is not a concern. That should be a concern. And user input and leakage information. We thought, okay, for the experiment, we correct a part of a percentage of the vulnerabilities. I didn't put all the results, but I just show you like 30% of the OpenSCADA. We fixed it, and then we run the experiment again. So we had two versions, and the correction, because it was a manual task, it took more than 500 hours from our team, a team of 7 actually professional coders at the graduate standing of Shiraz University, and PhD student, 6 graduate students, 6 master and 1 PhD student. And the experiments, so we first did a regression test. That was after we fixed the bug, we wanted to make sure if the functionality was okay, and then we checked it with OPCS protocol connectivity, without connectivity, that the functionality test was passed. I mean, the application worked in both ways. So as I said, we were lacking metric for assessing availability, so we came up with 3 metrics that are open to discussion, for sure. First, we thought, okay, load time. If a system is more available, then it should load faster. If a system is if a system uses less CPU and less RAM, so it has more resources available and it can use more resources. So the less CPU it uses and the less RAM it uses, it is less likely that it goes out of service. And we ran the experiment with OPC activated and OPC not activated. We ran several experiments. In the experiment 1, that was load time, we reached about 7% improvement, although standard deviation did not vary much. In the second experiments for the time interval CPU usages with OPC activated, we also saw a major improvements, and also OPC deactivated. Both of them we saw improvement. So now the question was, okay, based on the metrics you proposed, you say, okay, availability improved. Now how about security? So we asked a team of penetration testers to attack on secure version. In the unsecure version, they could create 7 SQL injections, 2 cross-site scripting, and they access the whole directory structure of users, and actually, which we call information leakage. In the secure, we had no information leakage with less number of same category of attacks. So in conclusion, we concluded that we can look at differently at the vulnerabilities, and we can improve security and availability at the same time with promising results of functionality, performance, and testing. The newer part of my talk, which is the more on re-ranking, was again this recently graduate student Reza Karimian, and one of my bachelor students that we worked on. Basically, what we thought we were focusing on very little attention on the issue. So we searched the literature. The number of publications on CPS and ICS related security are increasing enormously, and interestingly, our work got attention of Professor Goldman, and he also commented that he needed to see a finer categorization of vulnerabilities. So we checked the test beds that are created. Actually, 2 test beds in the study are my team test beds that were created. And we looked at the prioritization and risk assessment. And after almost 5 years of our research, we didn't see similar research emerging, and control control system or CPS or IoT, we didn't see it. So actually we started from our own base work and we focused on that. And as I told you, we reordered the vulnerability based on categories. But here we didn't go deeper onto CWEs by itself. We didn't check every single CW and re-rank it. We just changed the category. In the we also looked at other frameworks and other structures. So we proposed a new framework, and based on the framework, we had metric selection and weakness selection and data collection, and then seven new factors of technical impact, finding confidence, deployment scope, business impact, likelihood of discovery and likelihood of exploit, and prevalence for the new factors we inputted. As I told you, in the CW by itself, you have description, it talks about what languages it uses, it talks about the scope of the attack, and it talks about impact, how the vulnerability attacks. So each CW, it comes with a lot of descriptions, and we wanted to use those descriptions. We have 6 categories of information regarding a CW: the detection method, the description, the application platform, common consequences, and likelihood of exploit, and potential mitigations were all discussed, so we could use that. And interestingly, we found a very, very general weakness scoring system. But it is so vast that even when we talk to the people in the ICS CERT and to the people in MITRE Corporation, personal communication revealed some of the items they propose for scoring, they cannot easily be actually proposed. So this is to tell you what this research is, and it's basically, and what the metrics is this is like the business impact. They said, okay, if it is critical, give it 1, or if it's high, give it a 0.9, or medium, 0.6. But no data is provided in that metric, and no calculation method how to reach that. So we didn't have any of that. Moreover, when we got deep into this study, we only selected these 7. And for data reason, or we didn't know how to calculate, or we couldn't customize it for the ICS setting and CPS setting that we were using, we didn't actually use the features on the left. We just went on with the right. Definitely, I'm sure if with the help of AI methods, we can tackle more features, more relevant features, and come up with a better ideas. In this study, we used 4 industrial applications, and the 4 industrial applications, we ran static checkers, and we came up with 42 types of vulnerabilities. And we also used the 25 top vulnerabilities. So we wanted only to rank 67 CWEs only. Here, we didn't just focus our work on industrial software. We used the information image, and we also checked the guidelines, the industrial companies' white papers, reputable documents, papers, everything we could come up. And like interestingly, in technical impact in the SCADA team, they provided some numbers. So the MITRE Corporation gave some numbers for those modifications, but and we used them. I mean, we actually, for technical impact, what we did, we looked at like which part they attack and what are the impact, and based on the numbers, we wrote the numbers, we came up with the maximum, so we could get this feature. But for some other features, we had to come up with our own idea. So for finding confidence, we said, is it weakness or it can be utilized by attack? And we actually code reviewed the vulnerability, and we used stack analyzing tools and what the static analysis tool gives us, and we gave numbers. For others, we had to come up with formulas. We used TIOBE, like for deployments, we used TIOBE language rating, which is how popular it is. And the relevance, we also looked at the CWEs. And based on these 2, we came up with numbers. So I go over the rest of them. So we combine them. For example, for likelihood of discovery, if we static analysis, we could find it so it's easy, we get a big number. But if we had to run and check it dynamically, so it's difficult, we get it a lower number. Anyway, we combined these likelihoods, and recently we came up with based on the formula CWSS provided, we omitted those numbers that we didn't have valued, and we re-ranked the vulnerabilities based on a new system. So basically, the first rank belonged to CW 250, which is execution with unnecessary privilege. Means you have a full access of the system to run anything. So that's very dangerous, and it can cause severe problems. And so to assess what we did and to check whether what we found is good, we had to run the experiment on several settings. First, we did human evaluation, that is expert evaluation. I know this is not something AI people like to hear, oh, so it is very subjective, but we had no other way to assess the factors that we had no experimental data for. So the first phase was just to ask experts, cybersecurity, industrial control systems, people in industry, people in manufacturing, and software engineers, on our selection method and data collection and calculation and results. And in the second part, actually, we tried to see if the OpenSCADA framework that we use in our past experiment, we can run the similar experiment. We focused, we ran static analyzers, and we came up with a lot of warnings, but we focused on errors, the ones that severity were critical, severe, or error. And we checked the result. As I said, we had static checkers provide a lot of false positives. So we did a code review on the, and to make the code review not just a subjective person, we trained actually in my secure coding class that I try to tell everybody. I had this concern of secure coding, and it's been almost 6 years that I've been teaching the graduate course on that, and I try to train students so they can come up with that. So we spend 24 extra hours to talk more about CW and secure coding code review, and we check them by 12 students, 10 master students and 2 bachelor students. And after analysis of 658 by all these 12 students, we came up with 94 actual vulnerabilities. These 94 actual vulnerabilities, there were a fairly good agreement between, and it was a substantial agreement between the people. And we fixed the vulnerabilities. Actually, we fixed part of the vulnerability, 20%, 20 out of those 94. And we ran the experiments, as I said, similar to what we did with the previous experiment. We again looked for availability metrics. We again searched all the literature, but we couldn't find anything similar. I think this line of research needs attention, but we checked all those, and again, we found out that on secure version, in compared to secure version, has a lower availability and lower numbers in the load time. As you can see, it is faster for secure version to come up. We ran some exploits. This is the part of the code that is here. As you can see in the code, the meddev bars is actually maximum should be 3, but in contrast it gets 4. So actually they attacked this vulnerability and they wrote the exploit for it, so it crashes the system. So it was one that says these are vulnerabilities, and the malloc also in this code snippet was used. I'm finishing pretty fast. Yeah. I'm done in 1 minute.
That was good. We just had our time. We only have the window closes.
Yeah, no, just 1 minute. Yeah, just 1 minute. I'm done. So in the last, this is the type of vulnerability I say it's just for CPS, and they actually use resource consumption. I mean, they just wrote a program that consumes memory, and the malloc couldn't return, and it returned null. So null pointer, as you can see, it got a segmentation fault, and so somehow our vulnerability showed, and I skipped this. It's like the third type that was in Aryan, rank 3, and I conclude my talk. The proposed talk that I presented, the first time I'm presenting it, is the first attempt to reorder vulnerability based on CWE, and I hope, I look forward to collaborating with all you guys, and thank you very much for the time you spent listening to my talk. Okay, thank you very much.